Hello, Chemistry, Mr. McKee here with the final installment in our stoichiometry series, in which we incorporate density and volume into our calculations. So I want to begin by reviewing the concept of density here. Density in words and description is a measurement of how much mass you have in a particular area, okay, how much stuff is packed into a particular space. The mathematical formula we use is density equals mass, typically in grams, although it could be milligrams or centigrams, divided by volume, which is typically going to be in liters, although again, it could be milliliters, decaliters, whatever, okay? But most of our calculations are going to involve units of grams per liter. So the simple formula is density equals mass divided by volume. And you might recall some of that from one of our first labs of the year. Okay, so now that we've reviewed what density is, let's jump into the calculations involving density and volume. So a lot of these problems are going to be a bit more wordy, so it's really important to read carefully and reread carefully the question. So let me model that for you guys here. The reaction that causes cake batter to rise involves the production of CO2 from baking soda. NaHCO3, that's the formula for baking soda, reacting with an acid such as acetic acid, which is HC2H3O2. So what volume of CO2 gas will be created? So that's one thing we want to underline here. So that's what we're trying to figure out, what volume of CO2 gas will be created when 15.0 grams of baking soda is used. Okay, so we're trying to figure out a volume of CO2 when given 15 grams of baking soda. At the baking temperature, the density of CO2 is about 1.10 grams per liter. That is also going to be important, but not for a little while here. Okay, so after reading the question, again, rereading it carefully, we want to make certain that we know which parts of the equation we care about for a particular problem. So in this case, we care about this chemical here, which is baking soda. I'm going to abbreviate it. BS, have fun with that if you want. And we are also interested in carbon dioxide, specifically what volume of carbon dioxide is going to be made. So for this particular problem, we can ignore all of the rest of these chemicals, which are certainly involved, but are not relevant to this mathematical relationship that we are exploring here. All right, so recall that we can always divide our stoichiometry roadmap down the middle, and we can think about chemical A as being on the left side and chemical B on the right side. Hopefully you've noticed that we are always exploring a relationship, a mathematical relationship between two chemicals in these problems, never more than that at one time. Okay, so chemical A is always going to be the thing that you start with, and that in this case is going to be baking soda. And we've been given 15.0 grams of baking soda, which means we're going to begin right here, and we're going to work left to right across our stoichiometry roadmap. So our first conversion is to convert from mass of baking soda to moles of baking soda. And one thing we can do is identify what we're trying to get to. And if we read up here, we want to know what volume of CO2 gas is made. So we're trying to get all the way over here to the right. So again, in the midline, we convert from chemical A to chemical B using the mole ratio, which in this case is 1:1. So we're going from baking soda to CO2. And then we convert from moles of CO2 to mass of CO2 using the molar mass. And then we're going to use our density to convert from mass of CO2 in grams to volume of CO2 in liters. Okay, so I just mapped that out. You'll notice that I need to know the molar mass of both baking soda and of carbon dioxide for this particular problem. So baking soda, the formula is NaHCO3. Again, I've been abbreviating that as simply BS to avoid having to write that a whole bunch of times. CO2 is a little bit easier. And if we add up all the parts of NaHCO3, you should get a molar mass of 84.006 grams. And for carbon dioxide, 44.009 grams. Okay, let me know if you are having trouble with that, but we've done that quite a few times at this point in the year. All right, so now we are ready to proceed with solving the problem. So I'm going to use my roadmap. My starting number in unit is 15.0 grams of baking soda, and I'm trying to figure out liters of carbon dioxide. So in the order that I'm going to use the conversion factors, my first one is going to help me get from mass of baking soda to moles of baking soda. So that is going to be 84.006 grams of baking soda is equal to 1 mole of baking soda. So that's my first conversion factor. And again, that gets me from mass to moles of baking soda. Then I'm going to use my mole ratio from the chemical equation to convert from moles of baking soda to moles of carbon dioxide. That relationship is a really easy one in this case. It is 1 baking soda for every 1 carbon dioxide. So 1 mole of baking soda equals 1 mole of carbon dioxide. 1-to-1 molar ratio. It's a very easy one to work with mathematically. Okay, next in my roadmap, I'm going to convert from moles of CO2 to mass of CO2, and I'm going to use the molar mass of CO2 in order to do that. So 1 mole of CO2 is equal to 44.009 grams of CO2. And I got that number up here. Finally, my last step, I'm going to use the density of carbon dioxide to convert from mass of CO2 to volume in liters of CO2. So that density, which I get from reading the problem, is 1.10 grams per liter. So in other words, 1.10 grams of CO2 is equal to 1 liter of CO2. So I'm going to use that density as a conversion factor. So one thing I encourage you to do is to just put your units in before you even mess with numbers. So my starting number in unit, go here, but I'm just going to put the units in here right now. Grams of baking soda, which means I need to have grams of baking soda there. And my first conversion is from grams of baking soda to moles of baking soda, which means I need to have moles of baking soda there. Diagonals are always going to be the same. And this next conversion is from moles of baking soda to moles of CO2. Your roadmap can help you with this also. And that means I need to have moles of CO2 down here. And my next conversion is from moles of CO2 to grams of CO2, which means I need to have grams of CO2 down here. And my last conversion is from grams of CO2 to liters of CO2. So now you can go through here and cancel things out. Make sure you end up with the right units. Make sure that you're actually able to cancel stuff out. And this leaves us with liters of CO2, which was the goal. So now we just have to plug numbers in and do the math. So we have 15.0 grams. We have 84.006 grams of baking soda is equal to 1 mole of baking soda, We have a 1-to-1 mole ratio, which I get from the equation. Both coefficients are 1. And then for every 1 mole of CO2, it's 44.009 grams. And every liter is 1.10 grams per liter. Okay, now I just need to plug everything into my calculator. And what that should look like is 15 times 44.009 divided by 84.006 divided by 1.10, enter. So remember, we only want to hit enter one time. And when you do that, you should get 7.14 liters of CO2. That's how much carbon dioxide gas you would produce if you started with 15 grams of baking soda. Pause the video and see if you can do the